Hello, good day, and I am about to discuss the last part of the topic for the finals lecture, which is about routing fundamentals. So last time we were able to discuss about the services and protocols, which is part of the TCP/IP layer. So this time around, we'll be looking into the basic concepts involved in routing. So without routing, it won't be possible for any data to actually navigate through the complex system of the internet with its interconnected nodes and be able to actually reach its destination. So let's take a look at some of the important things that we have to remember when we talk about routing. So first we have what we call packet routing. So packet routing is actually the process of transferring a packet from source to destination. Now it might sound simple enough, but actually, as I mentioned a while ago, because of the web environment, of the web nature of the intermediary nodes that exists in between the source and destination, especially if the packet would be passing through the public network or the internet. Now, the primary device involved to be able to actually route is the router, hence its name. So, switches and hubs unfortunately do not have the enough or does not have the enough capabilities to actually do routing, as they only go up to the second level of the OSI layer, unlike the router, which goes up to the internet layer, which is level 3. Now, because of the web nature of the public domain in which a packet may pass through, there would be more than one possible, or more usually there would be more than one possible route for a packet to take. Now, one of the essential functions of a router is to be able to pick the best route among all possible routes. So we call this concept of determining the best possible route as path determination. Now, depending on the protocol used, there are many ways to come up with the best route. Because when we talk about the word best in best route, it's actually a bit vague. As what do we mean by best? So what specific things do we look into, or factors that we look into to say that a specific path is the best path? So we'll look into that later on. Now, we have to determine first, or we have to discuss first the two main types of routing according to how the packet would travel. If a packet would travel a specific route, regardless of the number of routes available, we call it as static routing. So we usually use static routing if the packet would only be sent within a very small or a simple network. So usually network administrators would configure the route specifically for that specific packet so that it would reduce the consumption of resources that would otherwise be used when we are using dynamic routing. Unfortunately, static routing is something that is actually quite hard, if not impossible, to be used inside or if the packet would be traversing the public domain or the internet. So usually, when sending a packet or data or any sort of information to the public domain, we use dynamic routing. So in dynamic routing, we let the routers, the intermediary nodes and the routers in between the source and destination to decide for themselves which path to take. Overall, the path that it would take from source to destination is chosen by what we call the path determination. As mentioned a while ago, the concept of best path depends on several things, as would be discussed later. So, as mentioned a while ago as well, if the static routing is for small and simple networks, dynamic routing was usually used for routing or for path that is actually for a very large network, such as the public network. Now, more often times than not, we have to actually send a specific packet from the source to destination through the intermediary nodes. So it might travel a few hops, if you will, or a few nodes or routers before it reaches its destination. So the process of transferring a single packet or a group of packets from one node to another is what we call packet forwarding. Now, there are times that there are several routers connected to a single router. And out of those routers, there might be more than one router that can be used to actually reach the specific destination. So, how does it know which port, which router it would send the packet to? Each router inside its memory actually has what we call a routing table. So the routing table is sort of a table or a database that contains all sorts of information that pertains to the connected routers, even the other routers connected to the intermediary routers. It might also contain specific routes going to a specific destination. So a routing table is actually a quite useful tool used by the router such that it will be able to actually send a packet from source to destination. We'll talk about the routing table later. Oh, right now actually. So inside the routing table, there are several fields. So if you happen to have a knowledge of what a database is, usually it's full of information with its specific route, and then it has its own specific field. Think of it like an Excel file sheet, if you will, that has several rows and columns. Each row and each column pertains to a specific information pertaining to a specific data. In this case, we're talking about routes and what specific interface we have to send the packet such that it would reach its specific destination. So these are the available data available in a routing table. So first we have the destination and masks. Technically they are two separate data, but they are used in conjunction to be able to identify the specific, either the specific IP address or the destination IP address, or at least the destination of the network segment. There are times that we can't send the packet directly to the host. Sometimes you can only know or determine which specific network segment it is part of. So what usually happens is we send it to the router that is managing that specific network, and that router would be the one responsible to send it to the specific destination. Next, we have the protocol field. So this indicates which protocol the routes are actually learned. So normally it's either UDP or TCP. Next, we have a preference field. Now, preference field suggests or assigns a value associated with a specific protocol. So for instance, there is a single route, and we can actually use two specific or two protocols or two different protocols in sending that packet. So whichever preference field is more preferred, then that is the one to be used. So each type of protocol has its own set of preference field. I'm not entirely sure if they can have the same preference data within it. If I can remember correctly, they must have at least different, or they must have different contents in the preference field. And this is the one used to decide which protocol is to be used. Next, we have the cost field. Now, for some instance that we have multiple routes, and those multiple routes have the same protocols used, therefore, it has the same preference. So, what metric do we use to determine which route we'd actually take? So, inside each routing table, each route is given a specific cost, which is contained in the cost field. Now, a specific number is assigned to the cost field pertaining to how better it is than the other routes. Normally, in a routing table, the lower the cost, the better the route is. So, more or less, if there are multiple routes having the same preference, the route that is taken is the one with the lowest cost. Again, just like with the word best, what do we mean by lowest cost? Well, it actually depends on the type of protocol used for routing, as we would see later. Another field shown or that can be seen in a routing table is the flags field. So the flags field contain a single set of information, but that information actually pertains to several flags. Flags, you might have heard of flags in microprocessor and microcontrollers, as that indicates status inside the microprocessor or microcontroller. So that's the same thing with the flags field. Each flag could only be either 1 or 0, high or low, indicating a specific status for that specific route. So the flags field contain 5 different flags. The first is the U flag or the up flag. This pertains to the availability of the router for that specific route. So for a specific route, the next router is actually associated with that route. The up flag would mention or would be the one needed to determine if the router connected to it is actually up and running. So if it's not running, we won't be sending the packet that way, even though it has the lowest cost, as it is temporarily or at the moment disconnected. Next, we have the G flag or the gateway flag. So if the gateway flag indicates if the next router or the next hop where we'll be sending the packet to is actually already the final destination or another intermediary node. So by looking at the gateway flag, we'll know if that's already the final destination or not. Next, we have the host specific flag. This indicates if the IP address for the destination is actually the IP address of the host or just the IP address of the network segment. As I mentioned a while ago, the destination could be the specific destination or the specific host already, or just the network segment where the host is part of. So the host specific flag is the one used to determine that. Next, we have D and M. D is a redirection flag and M is modified by redirection. So added and modified. Now, there are times, as part of the services of a router, it continuously updates its routing table. Depending on the type of protocol, sometimes it is refreshed during or after a specific amount of time. Or sometimes, in another type of protocol, it is refreshed or it is updated if there are changes in the route. Now, with that being said, if there is a new entry to the routing table, that means that if it was added by the ICMP was mentioned last time with the TCP/IP protocol suite as part of the protocol used usually for troubleshooting. So ICMP here also has the capacity to actually add a routing information if it was able to sense any changes or any uh, so by adding the redirection flags either add a new information or a new entry on the table, or it modifies an existing entry. So that's the difference between the two. Is it a new entry added by ICMP? Then you will see a status by the added by the redirection flag. If that entry already exists, but it was modified by the ICMP, then you'll see an activated modified by redirection flag. Next, or the last two data available in a routing table is the next hop value. When we talk about hop is the next intermediary node, or the next node where we'll be sending the packets to, or the next intermediary node in the route. It could be the final destination, or the final node, or it could be another intermediary node. So what's listed here is the IP address of that node, regardless if it's the final destination or not. Next, we have the interface parameter. The interface parameter actually dictates which specific port, which specific interface in the router the specific route is connected to. So multiple routes have multiple interfaces, and in order to determine physically where it is connected, the interface parameter is used. Now, as mentioned a while ago, when sending packets, the packet sent might be already the final destination or the final host or another intermediary node. So, if the packet sent is already the final destination, that means it is what we call a direct delivery. Now, if the packet sent is an intermediary node and not yet the final destination, we call it as indirect delivery. Now, as mentioned, we actually have several routing methods that we could use to determine what specific factor we are using to determine what is the best possible route. So first we have the distance vector routing protocol. So in the distance vector routing protocol, okay, one of its primary features is that it continuously updates all other routers, regardless if there is any change or not. So from what I can remember, it updates around every 30 seconds. And then each other router using the same routing protocol would also update all other routers, regardless if there's a change or not. Part of the distance vector routing protocol is our RIP, or routing information protocol. In RIP, the metric or the factor that it uses to determine the best possible route is the number of hops. So the fewer number of hops being the number of intermediary nodes it has to travel before it reaches the destination. So the fewer hops, the better, according to RIP, regardless of network traffic, distance, so on and so forth. So if it is the fewest number of hops in RIP, it shows or it chooses that as the best possible route. Also part of DVRP is CIDR, or Classless Interdomain Routing, and VLSM, or Variable Length Subnet Masks. In Classless Interdomain Routing, IP addresses are only seen having its network address and host address. Okay, so usually this is done to group several routes together containing the same amount of routing information. So this is used to reduce the amount of the routing information themselves. Instead of giving out single routing information for each single route, they're actually grouped together. Next, we have Variable Length Subnet Mask, or VLSM. VLSM or variable length is opposed to or as opposed to the fixed length subnet mask. When we had a discussion of subnetting, if you can remember, we can actually divide or we can use part of the host to be used as subnet masks or as to be used as a subnet to be able to divide the single network into several subnetworks of equal number of hosts. So we can divide this by, for example, we can divide this by 5 with equal 20 hosts each, something like that. But with VLSM, we can actually divide the network into subnetworks having different amount of possible hosts. So one network could have as much as a 128 host. Another one could have around 64. Another one could have 8 or any powers of 2, minus 2 if I'm not mistaken. So 126 and 62. As we have mentioned already that not all of the host addresses could be used. So with VLSM, it is possible. If in FLSM or fixed length subnet mask, the number of hosts must be equal for each of the subnetworks. When I say equal, the maximum number, not the actual number, but the maximum number of possible hosts that we can connect. Now, RIP, or Routing Information Protocol, actually has two versions. Not surprisingly named version 1 and version 2. So what's the similarities between version 1 of RIP and version 2 of RIP? So first, they use the same metric, hop count, as the primary metric of determining which route to take. Next, we also have the administrative distance. Administrative distance is a specific number assigned to a specific route to determine which route would be a better route or not. Okay? So the default assigned is 120 for versions 1 and 2. One of the main weaknesses or disadvantage of using RIP is that the maximum number of hop count that it recognizes is only 15. If a route has more than 15 hops, it disregards that route and only uses routes that has less than 15 hops. Both version 1 and version 2 uses UDP. When you say it uses UDP, it uses UDP to send out data to other routers. Remember that in RIP is part of distance vector routing protocol, which refreshes router or routing tables regardless of changes. And it sends those updates using UDP. So we have the similarities. What about the differences? So main difference of version 1 and version 2 RIP is that in its routing. So version 1 is classful, version 2 is classless. Okay? So in classful distance vector routing, it only uses 2. A while ago when I mentioned classless, I actually made a mistake. So when we talk about classless, it actually sees 3. So instead of because if it can only recognize the network ID and the host ID, that would be classless routing, or classful routing rather. If it's classless, it can recognize 3 layers or 3 parts: the network, the subnet, and the host ID. So in version 1, another difference, because it uses classful distance vector, it does not send subnet masks, unlike with version 2. When it updates, it also sends subnet masks as part of the information. Next is the mode of transmission. Version 1 uses broadcast. Version 2 uses multicast. We already mentioned broadcast and multicast difference in our previous discussion. So in broadcast, it means that the routing information is actually sent to all routers connected primarily through the router itself. But with multicast, it sends multiple signals, but it only sends it to intended destinations or the intended party. So if we have 8 other connected nodes with our router, if we cannot pick or choose which router to send our routing information to, and we have to send it to everything, that is broadcast. But if we can choose which among the 8 we send the routing information, that is multicast. If we only pick one, that's unicast. So version 1 is broadcast, version 2 is multicast, and it uses different addresses in sending those multicast and broadcast transmissions. Version 1 and version 2 also different in authentication. Version 1 doesn't have authentication. So routing information sent does not need to be authenticated to be accepted. But with version 2, it needs to be authenticated first before it is actually accepted. So it could either use plain text or MD5 or message digest 5. Among the two, MD5 is more secure, as plain text, when intercepted, the authentication method and the passwords and username used for the authentication could actually be read. With MD5, that would not be possible. Features: in version 1, VLSM and CIDR are not supported, and it is supported in version 2. VLSM again is variable length subnet masks, so we can only use fixed length subnet masks for version 1. For version 2, we could use variable length. For version 1, we cannot use CIDR or classless distance vector routing. We can only use classful routing. With version 2, that is supported. But both of this is actually inferior compared to link state routing protocol or LSRP. So in link state routing protocol, unlike distance vector routing protocol, in which the vector or the routing information is sent in a specific amount of time or after a specific duration regardless of any changes, link state routing protocol saves bandwidth by sending routing information if and only if there are any changes with the routing information in the protocol. And based on the information that has been gained from the link state routing protocol, the routers would actually recalculate routes and update its routing table. So it might change some of the fields as shown in the routing table we have discussed a while ago. It might even pick a new best route among the possible routes indicated. So part of LSRP or link state routing protocol is open shortest path first or OPSF. So this was developed by IETF in around 1988, and OPSF was designed such that it would react to changes in the network as quickly as possible and updating the other networks. So it establishes loop-free routes quickly, as that is one possible thing that might happen if we're using a poor routing protocol because of the web nature of the public domain or the public network. It is entirely possible that you actually create a loop that would actually start from where it would end where it actually started. Now, in order to prevent this, calculations have to be done by the router, and with OPSF, this could be done quickly. And LSRP actually do not base its best route with number of hops. It actually bases it on other metrics like network traffic and the latency, depending on the network administrator. And it is not hindered by the maximum 15 hops. So you can actually go beyond 15 hops. Anyway, that would be the last part of our discussion. As always, if you have any questions, don't hesitate to message me or to comment on the video. And also, please, uh, please stay safe. And if you can see any mistakes with the discussion, please put it on the comment section below. Thank you very much and have a great day.